Good. Okay, so as I said, we start with chapter 13 today, and it's about a prediction problem. So you have a y and you have x, and you want to see how this x will be mapped to y, and you can use it for predictions of future y's. And then we will go through different types of predictions, and then we will elaborate on the prediction errors and what is the best fit. So the prediction problem, when you do the prediction problem, it's called a predictive analytics, or some people use it, say it machine learning nowadays. And you have typically a y variable, which is called target, or you could call it outcome, or in the econometric sense, it is called dependent variable, and it is dependent on some x. So these x are predictors or independent variables. And usually you have a main data set, which is called original data set. This green part here that you can just split it to a training set and a testing set. So you basically train your model in the blue part and just do the testing in the red part. Some people also just use it as a sense of cross-validation that I will cover later. So you basically also can split the training set to also a training and validation. So you create your model, try to just use several ways of training the variables, and you test it with the validation there, and then at the end you do the final testing on the part of the data that was never shown to the model. And then at the end, the goal of any machine learning algorithm is to be good in the live data. So the live data is where you just go live and your model see things that it never saw before. So you should perform good in the live data at the end. So there are just some terminologies again. So people call this in sample. This blue part is in sample, and this testing part is out of sample. Also, sometimes it's out of sample is called the live data. So there's lots of terminologies depending on this on the use case. So what is the prediction model? So mathematically, there should be a function that maps the x that you have to a y. And we go with a simple linear regression today. So to just overview all the terminologies with the linear regression that we know all. So so a linear regression function is basically this formula. So you have different x, and you have some coefficients for them, and then for the training data, you can estimate this formula, and you find this B0, B1, and B2, and so on. And then you basically, when you fit your data there, you find these beta hats coefficient values, and then you use these beta hats for prediction. So if you have a new x, you use this fitted values to predict that this y hat that is the outcome of this prediction. So linear regression is just one type of the predictions that we could have. So basically, if our y variable is continuous, we use it. So we call it a quantitative prediction. So we basically are searching for just one number, and y is that one number. If our y is a dummy variable, so for example, having a heart disease, for example, 0, 1, then we should go for probability predictions. And the most famous regressions are logit regression. So you basically have a dummy in your y variable, and you regress lots of things on this, and it will give you a probability measure. So if it is then about 50%, for example, you say it will be 1, and if it is less than 50%, it is 0, something like that. And then there is a classification problem, there are many versions of the classification. So one version is a binary classification, which is basically this probability prediction that we had before. So for example, if you have two outcomes, for example, if you want to say if it is a male or female, so you regress something and you see if it can predict male or female. You could have multi-class classifications. For example, if you have pictures of animals and it could be cat, dog, or something else, so it could be multi-class. And we have also a multi-label classification. So for example, if you look at the picture, there is a dog and there is a car in that picture. So this it has multi-labels. So it should be able to classify labels. So for example, also a news article can be tagged with sport, a person, or a location at the same time. So this is a multi-label classification thing. So when we do these predictions and we find a y hat, this y hat could be different from the original y that is there, and we call that error. So the error is just the difference between what you predict and what it should be predicted. And this error has three components. So one part is the estimation error. So for example, in the case of a regression, so these betas that you find, they have themselves a standard error. So we are not sure exactly what is this beta. And this is, we know that for 95% of the time, it should be around this number, but we don't know exact number of that. So it creates some error itself in the prediction that we will make. And then there's also a model error. So for example, we could go for a better model specifications, for example, regressing this or having an interaction terms in the regression and so on. This errors is coming because of which we chose the wrong model. And at the end, there is one part of the error that is called irreducible error, or they call it also idiosyncratic error or genuine error. That is not, we cannot solve this error because it is either because there are some x that are unobservable in our database, we cannot have them to model. And also it could be because, for example, our y has a noise in the measurement itself. So there's no way that we can do anything about this error. And so people in machine learning, they use they use a function to basically tell the machine that it should optimize itself. So they call it loss function, and basically they map the error term to a number. And so basically, yeah, loss function translates the prediction error into the loss. And it's necessary to evaluate the quality of the predictions. And there are two characteristics of these loss functions that are important. First, how if it is symmetric or asymmetric, and how convex it is. For example, in this picture that you see here, this blue line is a linear function there. So, for example, if your prediction error is 5, the loss is also 5. And if it is 10, it is also 10. If it is minus 10, it is 10. Okay. Sometimes you want to put more emphasis on the positive loss. For example, that's why you could just shift it in a way that, for example, it will be going more rapidly up in the positive errors and less rapidly up on the negative errors. As you can see here in this, I don't know, reddish line. So it is asymmetric, but still it is convex. So it's going down to 0. So then there is no prediction error, it is 0, which is the best part. But in the positive realm, it goes more rapidly up than in the negative part. And then you can also have this green line, which is symmetric and convex. So you don't care if it is negative or positive error, you don't like both of that. The most famous example of a loss function is mean squared error. So basically, as you see here, you basically, if you have J observations, you get an average of the difference of what is predicted versus what it should be to the power of 2, and then you just sum them. And also the second famous one is root mean squared error, which is basically the square root of what you had in the MSE. Okay. Any questions so far? Okay. Yeah. So when you want to fit a regression or any algorithm, you need to minimize this loss. And the machine tries to find the best fit that minimize this loss. The problem is that there is a trade-off between two components of this loss. So you can, if you look at this formula, you can rewrite it in a way that you get a term which is, we call it bias, and I'll show you what's it exactly, and a term which is called variance. And if you're interested in the proof of that, this Wikipedia page has a proof. I just don't want to go to the mathematics now. Yeah, so you basically can go on with this expansion of this formula and then get these two terms out of that. So there's two terms in this mean squared error loss. And when you see the first part, we call it prediction error, which is basically the average of the error terms that you could have. And then there's a variance part, which is the variation of this model, the fitted model based on the new observations. So you could have a model that has a high bias, a low variance, and the other way around. So when you basically minimize the mean squared error, you need to find a sweet point between the having high bias or high variance. Okay. Here is just an example. So assume that we have this blue dots as a real data set. Then we can have just a line that fits all the points there. So basically, so there's no bias there. There's no error here in this model. But the problem with this high variance thing is if we get any new data here out of these lines, there's a huge variation in the new model. So basically, we call it also overfit. So it is overfitted here, and it will not be necessarily good for any new observation that we will find. On the other hand, if we have high bias, we get no variance here. So there's no variation here. So all the predictions are in the one line. Okay, no variation, but there is a high bias. So there are lots of errors for the current data here. So we didn't fit it correctly to the current data already. So that's why people are usually searching for the best solution in the middle. So here now I have a video from Josh Stammer. This is like a really nice guy. I really like his videos. So I think he shows it with a nice example. So let's watch this video first. And I hope you see. Let me share the computer sounds. I hope you hear that. Just tell me if you're not.
Imagine we measured the weight and height of a bunch of mice and plotted the data on a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain weight, mice don't get any taller, just more obese. Given this data, we would like to predict mouse height given its weight. For example, if you told me your mouse weighed this much, then we might predict that the mouse is this tall. Ideally, we would know the exact mathematical formula that describes the relationship between weight and height. But, in this case, we don't know the formula, so we're going to use two machine learning methods to approximate this relationship. However, I'll leave the true relationship curve in the figure for reference. The first thing we do is split the data into two sets, one for training the machine learning algorithms and one for testing them. The blue dots are the training set, and the green dots are the testing set. Here's just the training set. The first machine learning algorithm that we will use is linear regression, aka least squares. Linear regression fits a straight line to the training set. Note, the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. No matter how we try to fit the line, it will never curve. Thus, the straight line will never capture the true relationship between weight and height, no matter how well we fit it to the training set. The inability for a machine learning method like linear regression to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relatively large amount of bias. Another machine learning method might fit a squiggly line to the training set. The squiggly line is super flexible and hugs the training set along the arc of the true relationship. Because the squiggly line can handle the arc in the true relationship between weight and height, it has very little bias. We can compare how well the straight line and the squiggly line fit the training set by calculating their sums of squares. In other words, we measure the distances from the fit lines to the data, square them, and add them up. Psst! They are squared so that negative distances do not cancel out positive distances. Notice how the squiggly line fits the data so well that the distances between the line and the data are all zero. In the contest to see whether the straight line fits the training set better than the squiggly line wins. But remember, so far we've only calculated the sums of squares for the training set. We also have a testing set. Now let's calculate the sums of squares for the testing set. In the contest to see whether the straight line fits the testing set better than the squiggly line, the straight line wins. Even though the squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. In machine learning lingo, the difference in fits between datasets is called variance. The squiggly line has low bias since it is flexible and can adapt to the curve in the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for different datasets. In other words, it's hard to predict how well the squiggly line will perform with future datasets. It might do well sometimes, and other times it might do terribly. In contrast, the straight line has relatively high bias, since it cannot capture the curve in the relationship between weight and height. But the straight line has relatively low variance, because the sums of squares are very similar for different datasets. In other words, the straight line might only give good predictions and not great predictions, but they will be consistently good predictions. Bam! Oh no! Terminology alert! Because the squiggly line fits the training set really well, but not the testing set, we say that the squiggly line is overfit. In machine learning, the ideal algorithm has low bias and can accurately model the true relationship. And it has low variability by producing consistent predictions across different datasets. This is done by finding the sweet spot between a simple model and a complex model. Oh no, another terminology alert.
Okay, so I think so we don't need to go to boosting and baggings, but I show you some other things that could help you to find the best spot there. So now basically the question is so one way to just find the best model would be to add more complexity to model until we find the best model that could predict the current data without overfitting. And how we can do that? So first of all, if you take a look at this figure here, I hope you can see it, right? Okay, so this original data, so if you is the green line here. So if you add more complexity in the terms of linear regressions, for example, could be higher degrees of a polynomial or having more variables, for example. So we add more complexity to the model by adding a new X observation or having the X2 or X3 and so on of the same variable. We can see that in our original data, the root mean square error is reducing the more complexity we have. So basically, we're having more curvatures in our line at the end, and it will be a better fit to the original data set. Okay, but yeah, if you at the same time test it in the other data sets, you can see that it is basically yeah, there is until a part that this complexity also coming down for the test set, but after a while it will increase. So it is basically a sign of overfitting. Okay, there are three ways at least to understand when is the time that we are starting to go for the overfitting. The first one, so for example, we can check so in the case of a linear regression, we can check the R squared, adjusted R squared. So adjusted R squareds are, so they are the same R squared, but they're just adjusted to the number of coefficients that we use in the regressions, okay? There are two other ways that are much more popular. The most popular one is BIC, which is Bayesian Information Criterion or Schwartz Criterion. It is very similar to R squared. So basically, when you fit a regression line, you see the adjusted R squared and BIC and so on. They are all similar in a way that they have a penalty to the number of coefficients that you use for your regressions. And then you can see what is the optimal part here. So let me start with a Kaggle notebook that I just created. I think you have let me share it again in the chat. I think you have also on the course web page. So we start with the data set called housing data set. So it is like the price of some homes based on the area and some how many square meters the home has and some other options that the home has. And we just want to see how our fitting works here. So for the regressions here, I use the stat models, which is a nice regression model library. But at the end, I also use the Sklearn, which is the normal library for doing machine learning in Python. Okay, first I just read this housing data set. As you can see, we can see the price of a home, how big it is, how many bedrooms, bathrooms, stores, if it is on a main road, if it has guest room, if it has basement, if it has hot water heating, air conditioning, how many parking lots it has, and if it is a preferred area, and if it is furnished or unfurnished, okay? So to just be able to do some regressions, we need to convert all this yes, no, and these things to some 0, 1 dummy variables. So let's see how many observations we have. We have 545 observations. So what we do, we convert these yes, no things to 1 and 0. And we also, yeah, so let's do it first. Okay, so this, yeah, this is 1 and 0 here. And then finally, we also need to convert this furnished and semi-furnished to also some other new variables. So basically, we can do that with the get dummies comment. So if you say get dummies the furnishing status, it will give us, let me just do it separately. So it will give us 2 new variables, semi-unfurnished and unfurnished, with 0 ones. And then you can just add this new data frame to the previous data frame and drop this furnishing status that we had. So it will be like this at the end. And now we are ready for doing some regression analysis. Okay. Okay, so let's first just do regress price on area. As you can see here, you can see the dependent variable is price. It's an OLS model or least square model. And so it has an R squared here. It has an adjusted R squared. If it's statistic, you don't need it now, but you also get an AIC or BIC. Okay. And then this is like the fitted line with this intercept and this, yeah, this area here. You can open your microphone if you have questions.
I have a question here. How can we access to the results that these function give us? For example, can we have only the coefficient of area?
Yes, 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 we can.
As a single variable, for example, in a list or in something.
Yes, so you put the whole thing in a regression 1. This is a regression summary method that gives you this, but I guess there should be regression coefficients. I know, for example, R
it's
squared
reg 1, right? I think you saved it as
reg
1.
1. Oh, okay. Okay, so it has
You can use the .params method. I also googled it.
What was that?
The .params.
Params. Right. Yeah, okay. Makes sense. Yeah. So you can get the area, for example, I guess it's the second params. Yeah.
Thank you.
And so on. You can get the R2. Oh, yeah. R squared, I guess. Yeah. This or R squared adjusted. And yeah, BIC. Yeah. So the only difference is that for R squared, the higher R squared, the better fit it is. So basically, if you look at the formula for R squared, the higher R squared, the better it means that the regression line is fitted to the current data. And also the same for adjusted R squared, the higher, the better. For AIC and BIC, it is the other way around. So the lower, the better it is. So let me just show you the BIC formula. Yeah. this is the formula of BIC. So this K here is the model complexity, or in other language, you can say how many parameters you have in your model. So the more parameters you have, you get a bit bigger BIC, and this L here is very similar to R squared. So the less BIC better, the more complexity it will bring the BIC up. So at the end, you should search for a model that has the lowest BIC. And yeah, BIC, R squared, and AIC, they're all famous information criterions, but BIC is the mostly used in the machine learning language, I guess. So yeah, you get this BIC for regressing area on price. If you just increase the complexity of the model by adding more variables here, like bedroom, bathroom, stores, and so on, you get a new regression. So this is everything here, but you can just compare to the previous regression here. So the R squared previously was 28. Now it is 68%. So there's a huge improvement here. The adjusted R squared also increases a lot, because it was 28% and now it is 67%. Okay, so it means that adding these new variables help us a lot in fitting a better model without the fear of overfitting. Yes, again, question. The other question, no? Okay. Yeah. Okay, so now let's go for.
I do have a short question.
Sure.
Can you see the warnings? So basically, above your screen, the second warning, the condition number is large. I also had this in my case assignment, but in the first regression, you only used like one parameter, right? So how can that be that there is a strong multicollinearity issue? Is that a bug in the stats model API, or do you know where it comes from?
I have no idea where it does come from, but it's just
because we use only one parameter. So how can there be any multicollinearity issues?
Yeah, I think I always get this as well. I don't know. Maybe it is a bug, but
okay.
Or yeah, I don't know how it is calculated there. Do you get the same error if you use HC1 instead of HC0?
I haven't tried that one.
Yeah, so I mean, I have no idea that.
Maybe you can try HC3 or 4. That would be more robust, I would say.
What is H3 then?
I think it's a bug because yeah, it doesn't make any sense.
Yeah, I think the model is well specified with the higher FS statistic, basically.
Yeah.
No idea. Yeah, let's continue with the regression that we had. So we have this R squared here for having all the variables that we have here. We can now add a new term here, which is called the power 2 of the area. So we have area squared as well. And so let's see if it increase the R squared of the model. It increases actually. So this model, regression tree, is a better fit to the current data we have. But let's compare the R squared adjusted. You can see that although the R squared was going higher, the R-squared adjusted is going lower because we added a complexity that is unnecessary.
It's
Okay.
also higher, isn't it?
No?
In the second case?
Oh yeah, it is. Okay. Okay, nice. Let's see for the having the second and also the third thing. This one is still increasing. Interesting. Let's see how what BIC. So the BIC here was this. Oh, yeah, at least for the BIC, the first one is the best according to BIC. Am I? Yeah. So yeah, and there are differences between R-squared and the other metrics, and you know, the R-squared should be, I mean, all of them should be used for out-of-sample observation. What we do here is like just fitting the whole data that we have, which is not the greatest idea. Okay, so usually what you should do is you should split your sample to a train and test. That's what we are going to do now. And then fit the model on the training set, and then test the R-squared or the BIC and so on the test set.
Sazan, short question. Do you know whether there are any packages available for basically kind of automatic testing? Because what we are doing right now is just juggling with the parameters, adding them and removing them. So is there,
basically for linear regression, you don't need that. But in the follows, I show you how you can do it with the cross-validation. And basically for cross-validation, you will do it grid search. Okay, let's.
Yeah, okay.
I forgot to mention here that this notebook is basically a copy and modification of this original notebook. And this notebook, if you just go there, you can see a case of cross-validation with the grid search. That is basically what you're asking for at the end.
Yeah, okay.
Yeah, but for what I'm doing here is just want to show how it works on a normal linear model, and then you can go for much better data algorithms with more things to be tuned than just number of them like x's. That's why then you will need them. Okay, going back here. So the first way of finding the best fit of how complex the model should be is to using the models with the penalty for complexity, which were adjusted R-squared, AIK, and BIC. Okay, and they are applicable. So the good thing about BIC is it's applicable to all the other models, all the other prediction models. It's not only applicable to the regression models, but other than regressions, we don't see R-squared easily. Okay, so that's why BIC is very famous. Yeah, any question here for this part? Good. The second thing people can do is, instead of just looking at the R-squared of the regression, they do a split between the test and train, and this split is usually done in like 80-20 ratio. So you do 80% of your sample as training, and then fit the model there, and then check it on the test set. Okay, how we can do that? So first, for the sake of simplicity, we are just looking at the area and the effect of area on the price. Okay, so we just get the data frame of the area and price, and we want to see this is like the scatter plot of area on price, and then we use Sklearn here. Scikit-learn is a very standard library for doing machine learning in Python. And it offers a train test split method that we are going to use. So we just say, okay, split the train and test set for this data set, for this data frame, and the size of train set should be 80%, and the test set should be 20%. And we also set a random state of 10 to make sure that if I do it here, you'll do this, you get the same result also in your PC and my PC. So the randomness is just yeah, it's controlled here. So let's see. Here you can say now out of 500 something observation we had, now we have 436 for the training purpose and 100 for the testing purpose. And then what I do here is just create a NumPy object here. So I said the DF train should be X train, DF train price is Y train. So I just find the X and Y, and the same thing for the test set. So the X of the test set is just the area, and the Y of the test is the price. Okay. Now I'm just going to test until so for a polynomial until higher degrees. I want to see until which degrees I can add complexity and it still measure the fit properly without overfitting. Okay. So again, so for the training set we have 436. And then just want to check here for degrees of 1, 2, and 3, and just want to fit the line here of the area on the price and see how well it is fitted there. Okay, so there is a pipeline argument in the Sklearn. So for example, I want to say that I want to have a polynomial feature of degree 1, 2, 3, and then I want to add it as a linear regression. So this pipeline is just creating the whole thing there. And so the model is getting things, bring it to the polynomial that you want and fit it as a linear regression. And we fit the model with the trained models, okay? And then we predict it for the test at the end, okay? I just want to show you this, so you don't need to do this part of coding yourself. And so this is what you can see here. So the yellow line for the train set, it is this line, and the same line if it applies to the test data, you can see that it still gets something. Degree 2 is and 3 are very similar, so the green and red parts are very similar. They also fitted here, and the same line is going to be shown here with just the test data is different from the training data. And then we can see how well fitted is in the right figure. Okay, so I'm just going to ask for each of these 3 degrees, what is the R squared in the train and what is the R squared in the test set. For the first line, you can see for the training set, it's 28% R squared here, 30% R squared in the test set, which is actually in the test set, it is better fitted. So we increase the polynomial degree and we get a better fit in the train set. So 33% here, also 33% here. I guess if we get more digits, it will be an improvement for sure. But when we look at the training set, the test set, we see that it reduces. So the best model is just the first degree here, according to our train test split. Okay. Yeah, although if we were just looking at the training sample, the best model would be this, right? Yeah, so we can say that, okay, we just go with this. And this is this is the model we get without overfitting. Okay, any question here? Cool.
Still the linear regression is the best model, right? Here.
Yes. Basically, this is the result that we got here.
Okay.
So based on the test set, the best thing is just the glue bomb. Okay. Now we could go for a better version of test and train split, which is called cross-validation. There is also a better video than what I can explain here. So that's why let's go and watch this video again. And yeah.
StatQuest, check it
Yeah,
out.
this guy is
Talking
crazy.
Okay,
Yeah.
let's start with some data. We want to use the variables chest pain, good blood circulation, etc. to predict if someone has heart disease. Then, when a new patient shows up, we can measure these variables and predict if they have heart disease or not. However, first we have to decide which machine learning method would be best. We could use logistic regression, or k-nearest neighbors, or support vector machines.
But basically, here the case is to compare different models, but you can also have same model with different specification when you do cross-validation.
And many more machine learning methods. How do we decide which one to use? Cross-validation allows us to compare different machine learning methods and get a sense of how well they will work in practice. Imagine that this blue column represented all of the data that we have collected about people with and without heart disease. We need to do two things with this data. One, we need to estimate the parameters for the machine learning methods. In other words, to use logistic regression, we have to use some of the data to estimate the shape of this curve. In machine learning lingo, estimating parameters is called training the algorithm. The second thing we need to do with this data is evaluate how well the machine learning methods work. In other words, we need to find out if this curve will do a good job categorizing new data. In machine learning lingo, evaluating a method is called testing the algorithm. Thus, using machine learning lingo, we need the data to 1. Train the machine learning methods, and 2. Test the machine learning methods. A terrible approach would be to use all the data to estimate the parameters, i.e., to train the algorithm, because then we wouldn't have any data left to test the method. Reusing the same data for both training and testing is a bad idea, because we need to know how the method will work on data it wasn't trained on. A slightly better idea would be to use the first 75% of the data for training, and the last 25% of the data for testing. We could then compare methods by seeing how well each one categorized the test data. But how do we know that using the first 75% of the data for training and the last 25% of the data for testing is the best way to divide up the data? What if we use the first 25% of the data for testing? Or what about one of these middle blocks? Rather than worry too much about which block would be best for testing, cross-validation uses them all, one at a time, and summarizes the results at the end. For example, cross-validation would start by using the first 3 blocks to train the method, and then use the last block to test the method. And then it keeps track of how well the method did with the test data. Then it uses this combination of blocks to train the method. And this block is used for testing. And then it keeps track of how well the method did with the test data, etc., etc., etc. In the end, every block of data is used for testing, and we can compare methods by seeing how well they performed. In this case, Since the support vector machine did the best job classifying the test datasets, we'll use it. Bam! Note, in this example, we divided the data into 4 blocks. This is called 4-fold cross-validation. However, the number of blocks is arbitrary. In an extreme case, we could call each individual patient or sample a block. This is called leave one out cross-validation. Each sample is tested individually. That said, in practice, it is very common to divide the data into 10 blocks. This is called 10-fold cross-validation. Double bam! One last note before we're done. Say like we wanted to use a method that involved a tuning parameter, a parameter that isn't estimated but is just sort of guessed. For example, ridge regression has a tuning parameter. Then we could use 10-fold cross-validation to help find the best value for that tuning parameter. Tiny bam! Hooray! We've made it to the end of another exciting stat quest.
Basically, this tiny bam at the end is what we are going to do now. Yeah, so to just summarize, basically, yeah, we do like a 5-fold or 10-fold cross-validation. So each time we use one set for testing and the rest for the training. And then at the end, instead of having only one mean-squared error, we have like 5 or 10 and get the average of them. And then we can see which model is better at the end with the lower MSE or RMSE. Okay. Yeah, what we are doing here is just a quick recap. What we are doing here basically is, yeah, we basically this is already set. We use from Sklearn again a method called k-fold, and there is a cross-value score that does everything automatically for us. But let's first do it. Yeah, let's first do it manually. So we defined an LM as a linear regression. So this is the model that we are going to use. So we could just use regression trees or whatever, neural networks and so on. But we are going with the linear regression here. And we have a k-fold with 5 splits. So we have 5 splits shuffled through and random state 100 to just get the same random states every time we run the code. So if we say this, then for each fold we can say fold split housing. So there should be 5 folds, and for each 5 folds, it will give us what should be the train index and what would be the test index for this housing data set. Okay. So basically we say, okay, training and the test should be those indexes that are in the train index and those indexes that are in the test index. So we get 2 data sets here. And then we fit the model on the trainings. So we fit this linear regression on the training without the price as X and just the price as Y. And then we see what would be the R squared on the test set. Okay, so we train it on the training and then get the score on the test set. Okay. So we have 5 folds, and then yeah, so for each fold we get this 68%, 66, 66, 64, 62, and then we can get an average of them. Basically, just averaging them and get the average of how good is this model. Okay. If you want to have it automatically done, or if you want to have more flexibility over what kind of things you want to do, you can just use the cross-value score function here. You can say, I want to do cross-validation on a linear regression model with the X being everything except price, and the Y being just the price. And the scoring should be R squared, and then I use the folds that I created here, okay? Can do that, and you can get the same R squared here, okay? You can, instead of R squared, use mean squared error, or there are 20 more kind of scores that are available that are people using in the machine learning. So you can do the same here. And you can get the average directly, so you can get the mean of them. So without this mean, I get 5 mean squared error, and then I can get the average, which is this number. And yeah, just one small note about negative mean squared error. So it is like just negative of mean squared errors. That's why it is negative. So the closer to 0 it is, the better the model is. Okay, so the mean squared error should be 0 in the best way. And the R squared, the higher the better. Okay. Now let's go back and see what is the best degrees for having area in our model. Okay, so we do the cross validation again with degrees 1, 2, 3 for the area. So we have X as the area here, and we want to explain the price, and based on R squareds. Okay. You can see here, degree 1 has the highest R squared, and then and degree 2 and degree 3. So you can see already degree 1 is the best here. You can do it with mean squared error as well, easily. You can see here is the lowest, so the closest one to 0, which is again showing, yeah, degree 1 is best here. You don't need to go for the complex models there. Okay. This is basically what I wanted to cover here. There was one question asked by Philip, so that's why I'm going to also show it. So in reality, the cross-validation works for very complex models that they want to, for example, you can check, you want to tune some parameters. And for example, assume, in this case, we just wanted to see what is the best degree of having the polynomial there, but you can just do it for higher, for more complex versions. So basically you can do a grid search here. So basically for all the folds, you do things several times for several types of the parameters. And this is, so this hyperparameter that we had, for example, is the degree of the polynomial, could be done like this. And then we have a 5-fold cross validation, and you can have 14 variables, 14 different kinds of degrees, and then we can test here. Okay, you can easily say that this is the hyperparameters to be tuned, and then there is a function called grid search in the Sklearn, and then you can say, okay, I want to have this estimator, and this is the hyperparameters that I'm searching for, and the score that is important for you is R squared, for example, and then you have the cross validation there. Okay, and then it shows you what is the optimal version. So you can see here the results of this cross validation, this 14 times cross validation, and then you can get the mean test score on all of them. And then you can see, for example, the best is here, and then the variable to select is 13. So here in this case, he wants to see how many variables should be used. So how many, if the area or the number of bathrooms and so on should be important. And then the best model that he found is the maximum features, like the 13, all the 13 features in the X data should be used. Okay. Yeah. So it's basically what I wanted to cover today. And so let me just stop this.